Very well. So today we consider the last important part of Prolog, which is cuts and negation as failure. So yeah, we're going to just revisit what cut is, how we can use it. We can use it both for efficiency and to sort of fix overlapping solutions or overlapping branches. And then we're going to discuss how negation in Prolog works and what is negation as failure. So here's a very abstract example that we're going to try and work with just for brevity. So here we have a predicate P, which is true whenever A of x is true and B of x is true, or if C of x is true. Okay. Now here A is true for 1, and both B and C are true for 1 and 2. Okay? Now, when we ask Prolog what P of x is, right? I mean, when is P of x true? What solutions does Prolog provide to us? Okay? Okay. Right. So the first answer is very easy to find, like, right? That's if A is true, well, A is true for 1, so 1 it should be a candidate solution. B of 1 is also true, so that matches. But then A is not true for anything else, so we try the second branch, right? And we see when P of x is true whenever C of x is true, and we get one more 1, and we get 2. Okay, so these are the answers produced by Prolog. Now, here we have sort of 1 extra 1, right? And sometimes that's unwanted, or maybe if A is true, we don't want to go into the second branch at all. So there is this operator which looks like an exclamation mark, and I mean syntactically it is an exclamation mark. And if we use it here right after A of x, then now P of x produces just one solution. X is equal to 1. So what happens here is this exclamation mark is called the cut operator, and it's used whenever you wherever you could place a predicate, you could place this operator, and this operator always succeeds, so it's always true, but it has a side effect, right? And its side effect is that it affects our search tree, or how we are going to traverse the search tree. So it does two things. First, it commits variable substitutions that we have selected when we pattern matched with the head of the current predicate, currently defined predicate. So exclamation mark here is defined as a body of P of x. So if we enter this, this line of definition for P of x, and we reach the exclamation mark, it means that whatever pattern matches have been done at the head of this, so when we did P of x, those are committed, which means that they will be permanent now. And whatever variable substitutions we achieved from, like, in the body of P of x up to this point are also committed. So you cannot have any changes to those as well. So let's see on this particular example. So for now, we're not talking about how to actually use it. We're just considering this example, how it works, okay? Just the mechanics of it. So again, let's see at the variant of this code without the cut operator. So like we discussed, we have P of x, and then there are essentially two possibilities for P of x, right? The first line and the second line. We have a choice here to be made. So we go into the first line, and now we have to compute A of x and B of x, right? That's our current goal. Okay. then a of x can be matched with the one fact that we know, that a of 1, right? And here x equals 1 is the variable substitution that happens, right? Then we have to check b of 1. That is obviously true, so we'll end up with true. And then if we need more solutions, we backtrack, right? We backtrack and we go to the second line of definition for p of x. Here we have c of x, and again, it's either c of 1 or c of 2, right? This is the tree. What happens if we place the cut operator? So again, up until we reach the cut operator, the picture is exactly the same, right? We want to figure out a of x. A of x can be true if x is equal to 1. Here's our variable substitution. We'll reach the cut operator, and at this point, we commit all of the choices for variables that we've made up until point, okay? So what we effectively do is we cut this branch that was previously possible to reach, right, with backtracking. After we reach the cut operator, it is now no longer possible to backtrack and go to that branch, okay? And then we just continue. B of 1 is true, so this is true. There is nowhere to backtrack, and so this is the only solution that we get. Does this make sense? Okay, very good. So here's a more complicated example. Again, a little bit abstract. Yes? Yes. Well, we'll lose 2 solutions. Yeah, exactly. So here's a more complicated example. So here we have A, which is true either if B of x is true or it's true for 1. Then B itself is true either if both D and E are true for x, but there is a cut operator used in the middle. B is also true for 2. And D is true for 3 and 4, and E is also true for 3 and 4. Okay? So let's see how this works. So A of x, to understand if A of x is true, we have basically 2 possibilities, right? The first and second lines of definition. We first try the first one and see if B of x is true. Now, B of x, again, has 2 branches, right? We go into the first one, which is, well, B of x is true if D of x is true, then cut operator E of x is true, right? Okay, and then when is D of x true? Well, D of x, well, here we have 2 branches again, because D of x can be true in 2 situations, right? If D is 3 or if D is 4, right? So if D is 3, then we have x is equal to 3, and then we need to check this goal. We reach the cut operator, and what happens here is we cut, well, what do we cut? We cut all of the branches that are above the cut and below the predicate where cut is used. So the predicate where we use cut is B. So we're going to cut all of the branches starting from B of x and up to the point where we have cut. So we'll cut these 2 branches, okay? Notice that the branch that is above B is not cut, because it's outside of the predicate that we defined using cut, okay? This is subtle, but it is very important. We're not cutting just all of the branches, we're only cutting those in the currently defined predicate, where cut operator is used. So now here we commit to the choice that x is 3. We check that E of 3 is true. We get that this is true. Perfectly fine. We backtrack, and now because we have cut the branch where x is 4, and we cut the branch where x is 2, we go to the other branch of A where x is equal to 1, right? We check, this is true, and we get 2 solutions. Okay? Does it make sense? So this is how cut operator works. It cuts branches, but it only cuts branches that stem from the predicate that used this cut operator, moreover from the specific line where it's been used, right? And it only cuts branches above it up until the point of entry to that line. Okay, so now how do we use cut, and why would we want to use cut? Well, one idea is to use cut to improve efficiency of programs. So here's one example. It's a very simple example. This is a predicate that computes the maximum of two values. So we have three values, x, y, and z, and z is the maximum of x and y, right? So if x is greater than y, then the maximum is x, right? So that's what the first line is, this definition is about. Now, if x is less than or equal to y, then y is the maximum, right? So this is a possible definition that we can use for maximum. Now, it works perfectly fine if we have 3 to x as arguments to max. What happens? Yeah, so x is equal to 3, right? But a more interesting question is how exactly do we arrive at that answer, and are there more answers, right? We try the first line, yes. We see that we can match x with 2, x with 3, right? So x is the third argument here in the query is a variable. So we can pattern match it with both the first argument and the second argument. So looking at our two lines, both heads of these clauses can be used to match with the arguments, right? So we try the first one first. We match x with 3, and then we check, is 3 greater than 2? That is true, so this is a possible answer. So this is a valid answer, we return it. But then if the user asks us, well, are there more answers? Then we backtrack, we see the second line of definition for max, right, the second clause, and we can now match x in the query with the second argument, 2. And then we check, okay, is 3 less than or equal to 2? Now that is false, and so somebody returns as false. But you can hopefully see that we have checked two things, right? We have checked that 3 is greater than 2, and then somebody asked, when backtracking, we also checked if 3 is less than or equal to 2, right? But we don't have to do that, because if we know that 3 is greater than 2, we don't have to check if 3 is less than or equal to 2. Right? So one possible fix here is to add a cut operator right after we checked that x is greater than y. Right? Now this cut will completely remove from the search tree the second line, right? Now notice that if x greater than y fails, it fails before the cut happens, so we still have backtracking there, right? So it still works. Now, still you might say this is not super efficient, right? Why? So if we have like max 2, 3x, right? We'll check if 2 is greater than 3, fail, and then check if 2 is less than or equal to 3. So we are again doing 2 checks just for one of the cases, right? So another possibility would be to say, well, if we have already checked that x is greater than y and that check failed, right, then we definitely know that x is less than or equal to y. So we can just remove that check from the second line entirely. Okay? Now, so this is a definition of max that is, well, has maximum efficiency for max in Prolog. Okay, so now let's compare these three definitions of max. So the first one doesn't use any cut and is completely declarative, right? So you just define when this predicate is true, and it is very easy to check well, if this implementation is correct. So there's no cat. It's very easy to check with your eyes, but it's not efficient. And of course, this is a very simplistic example, but you can imagine there are way more complicated programs that you will have to check with your eyes. Now, the second version is what's called a green cut. Now, a green cut is a cut that can improve efficiency. In this case, it does improve a little bit, right? But it is also safe to remove. If you remove this cut, the meaning of the program does not change, only the efficiency of this program. Okay? And now the last one is what's called a red cut. It also improves efficiency here, right? But it is unsafe to remove. If we remove the red cut in the last definition, then, well, now we have always x, y, y. If we put like 3 values where the third value is equal to the second, then that will always be true, right? So red cut has to be used with extreme caution, right? Do you understand? Yes? That if I remove the red cut, then the meaning of max changes significantly. So for example, 322 becomes true. Right? Okay, so let's repeat that. If I remove the red cut in the last definition, then the second equation tells me that 322 is true, right? And I can reach that equation if I do not have cut. Okay? Does anybody have questions about this? Sorry? Of course. Of course. So the question is, does the position of the cut affect anything? Well, let's see. Is there a? Not sure which whiteboard I can use. Probably this one. Okay. Can you see here? Is it fine? Okay. So we have max of x, y, x when probably I will have to do it also like this. When x is greater than y, and then we have cut, right? And then we have max of x. So which definition would you like to try here? The red cut or green cut? Okay. So for the green cut, we have x less than or equal to y. Okay, so here you're asking, does the position of this cut matter? Okay, let's see. What happens if we put this cut before this, right? Okay, so put it before. So we have cut and then the check. So if this happens, then suppose we have three, let's have an example. We're computing max of 3 to x, right? So 3 to x. So x, this x becomes 3, right? Let me actually change this to z just to make sure that you do not confuse the variables. So z, 3 to z. So x is 3, y is 2, and z is the same as x, so it is 3, right? Then we cut, meaning that we commit to the choices of variables that we've made, right? We can now no longer change what z is. So it's always 3. Then we check, is 3 greater than 2? That's true. So we succeed and we output z is equal to 3, right? So everything seems fine. Now let's check the other direction. 2, 3, z, right? What happens here? Well, now again, we go into the first line. We see, okay, x is 2, y is 3, and z is the same as x, which means it's also 2. And then we check, okay, is 2 greater than 3? Is it? No, it is false. So we want to backtrack, but we can no longer backtrack because we have committed to the choice of z is equal to 2. Does it make sense? Now, so putting cut before before this check does not work. If we put it after, then it allows us to backtrack here. If this fails, we backtrack and we use the second equation. And we only commit if we have performed this check. Does it make sense to everybody? Is there a question? Okay. Here, for this definition. So when we do 2, 3, z, okay, so what happens? Well, we have a branching, right? We either have max 2, 3, 2, where z is equal to 2, right? Z is equal to x, which is equal to 2, but I'm oversimplifying a little bit. Or we have max 3, 3, right? This is for the second equation, where z is equal to 3, right? And this reduces to this goal. X, well, x here is already 2, so we check 2 is great. I don't think this is visible to anybody. Let me try to fix that. Try to be technological. So I think this is very important. And can I do this? Okay, very good. So you can see it, right? Everywhere, I think. Yeah. So again, we have max of x, y, x is true whenever x is greater than y, and then we have this cut, and then max of x, y, y is true if x is less than or equal to y, right? Very good. And now the question is, how do we backtrack if we have query max of 2, 3, z, right? So we have 2 branches. One branch is for when z is the same as x, which is 2, and the other branch is when z is the same as y, which is 3. So here we have essentially max 2, 3, 2, and here we have max 2, 3, 3. So in this case, we're using the first equation, so we simplify that to 2 is greater than 3 cut, and here we will have, well, let's get there when we get there. So we first try the first one, 2 is greater than 3, and then cut. So this is immediately false, right? Because this one is false. Now we do not get to cut because this is already false. We don't have to get to the cut. So it doesn't really matter what happens after 2 greater than 3. This means that we can backtrack and go to the second line, right? Where we check that 2 is less than or equal to 3, which is true, right? Right. So if we use if we have the second or the third variation that we had, which was like this, right? Then we remove this check essentially, and we just immediately go to true, right? So that's what happens. And the question is, why does this still work if we have, on the other hand, so if we change this, these numbers, right, to some other numbers, for example, if we have 4 and 1, right, then again, we have two options of either z is 4 or z is 1, but we only first check the first one. So it's 4, 1, 4, right? And then we check if 4 is greater than 1. That is true. So we reduce to just the cut, right? And then this is obviously true, but also because we're using the cut here, we're cutting this branch. And so we're never going there. That means that even though this equation, if we just look at this fact on its own, it seems that max of 4, 1, 1 is also true, right? But because Prolog has a certain order in which it traverses the solution space, and because of how the cut works, this is no longer a valid solution to max. Does it make sense? Okay, any more questions? No. If you query for max of 4, 1, 1, yes, it will not match with the first one exactly. Yep. So this is not the correct implementation of max. How do we fix this? No, we don't want to. So if we still want to keep just one check, how do we fix? So this is a very good observation. This implementation of max is not correct as a predicate. So if we want to compute the maximum, it works correctly. But if we want to check if a certain value is the maximum of two other values, it doesn't work correctly. Sorry? Why not? Well, what happens here is we try to match, we try to use this head, right? So we try to first match the head of the first line of definition. But that line implies that the first and third arguments are the same. But if we provided the different arguments, they're not the same, so we cannot use this line at all. Okay? So we're immediately trying the second one and failing. Okay, very good. Very good observation. Now we have to fix it. How do we fix it? Sorry? Make it a green cut. Yes, that's one solution, but it's still, we want to still be efficient. We want to just have one check if possible, right? One check greater. Huh? No, a green cut is sometimes going to perform one check, but if we go to the second branch, we'll perform the first check and then the second check, right? So how do we fix this without introducing any more checks like less than or equal? No, there's a simpler solution. Yeah. So exactly. So what the problem was is that in the pattern immediately we matched that the first argument and the third argument are the same. But what we really want to do is we want to first check whether the first argument is greater than the second one, and only then pattern match the first and the third one. So what we do is we introduce the third variable for the third argument. Now, of course, we're not done yet, right? But now what happens when we call max of 4, 1, 1? Well, now we can go into the first thing, right? In the first line, we can go to the definition, to the check x greater than y, right? That will succeed. We will commit to this line, and then we need to finally do something else, right? So we need to, oh, z is equal to x, yes. It doesn't really matter here because we're dealing with numbers that we compare anyway. But if we have other things that we can compare and we want to compare other things other than numbers, right, then unification is probably what we want to do, not the not is. Okay. So now this works and this fixes. Yes, Anatoly, do you agree? Is this now fixed? But unification is just your, I mean, if you go down to how it's going to work in the computer, this is just a reference. So, and this kind of unification is the simplest possible one. Yeah, but you have to put solution anywhere. So we still had unification, but we had it in the head. Now we put it at the end after the cut. So originally we had max of x, y, x. Since we're using these two arguments here, we're actually performing unification of whatever is provided to us as inputs, right? And here we're just postponing that unification until after the cut. So it's the same operation, the same complexity is just happening later, which is more correct. Okay? Does it make sense? Okay. So question to you. In this implementation, this final implementation, is this cut green or red? So to understand if a cut is green or red, you imagine the same code but without the cut and see if it has the same solutions as the code with the cut. Of course, yes. If we remove this cut, then we'll have any triple of numbers where the second and the third are the same as a possible solution, such as 4, 1, 1. Okay. Very good. Very good. Let's go back to here. Okay. Yeah, so we now know green cuts and red cuts. Okay, so here's another example of where you would want to use cuts. So here, this is a predicate that we defined in the last lab, I think. Yeah, so it interleaves two lists. And a very natural base cases, two base cases for this predicate are when one of the lists is empty, you just return the other list. And if you run the predicate on something like interleave list 1, 2, and a list of AB, then you get two solutions which are identical, right? And that happens because the base cases here are actually, in this particular case, when our lists are of the same length, the base cases overlap. Both of them work. And in Prolog, because we do the backtracking, we try all the possible solutions that we may find, whenever we'll reach the base case where both lists are empty, we actually have two facts that satisfy this, right? And so that's why we duplicate our solutions. So to fix this, we can use cut. So in the first line, for example, we can say, well, if the first list is empty, then we unify the second and the third one, and we cut, meaning that, well, that's it. We know the solution. We don't have to check any of the other definitions for interleave, right? And if we define it this way, now we have only one solution. Okay, so this is a way to sort of cut down on duplicate solutions. Okay, so now let's talk about the last thing, which is negation as failure. And the idea is pretty simple. So here we define a predicate called not member, which takes two arguments, and it checks whether the first argument is not a member of the second argument, which is a list. Right? So if we have an empty list, then anything is not a member of that list, right? Because it has nothing in it. Now we can define it in the following way. If the list is not empty, then it at least has a head. If it has a head, and this head can be unified with our element, then we fail. Now, fail here is a special operator again that just fails. It's just like false, right? What's important for us here is that we're using fail in combination with cut. This means that we commit to, which means that we're not checking any other lines of definition for not member, right? So if we know that the element that we're looking for is in the list, then we fail immediately, and we cut right before it to make sure that we do not backtrack and find some other solution. Okay. So this is how we use fail, and then finally, if we have reached this third line, it means that the first two have failed, right? Which means that the list is not empty, but also that that X did not unify with H, right? Because this is the only place that could backtrack to get us to the third line, right? So when we reach the third line, because of the cut and fail, we know that X is not the same as the head. And so the only thing that we need to check is if X is also not member in the tail of our list. Okay, does that make sense? Sure. So if the list is empty, the predicate is true, right? If the list is not empty and X is equal, it can be unified with the head of the list, then, well, the predicate is false, right? So we say fail. But if we do not use the cut, then we will also try the last line, right? Which we do not want to do. We want to say this is false and that's it. Do not look for any other proofs that this is true. Yes? No, we can actually have X with X and X and remove this H equals X and just have the cut and fail on the right. Yes, that's also possible. So the question is, can we use X here and remove this unification? And yes, we can. Okay, very good. Now, tell me, is this cut red or green? How many of you think that this is a green cut? How many of you think that this is a red cut? Okay. And others are undecided. So this is a red cut, again, because if we remove this cut, then this predicate will always succeed. right? Because if we remove the cut, then the second line doesn't really matter to us, because if the list is not empty, we will just do the recursive predicate, and we will reach the empty list eventually, and we'll return true, right? So if the cut is not there, then the second line does not really matter. It only matters because of the cut. Okay, very good. So if we call not member for 2 and list 1 to 3, what happens is we realize that the list is not empty. So we try the second line, right? We see if 2 can be unified with 1. It cannot, so we backtrack, go to the third line, right? Unify 2 with 2, do the recursive call, unify, and then go again to the second line, unify 2 with 2. They can be unified. We go to the cut, so we cut all of other branches. We are not going to be backtracking anymore, and we fail. Okay, so we return false immediately. Okay, what if we call 4 not member with 4 and 1 to 3? Well, we go to the second line. We cannot unify 4 with 1, so we go to the third line, do the recursive call. Go to the second line again, unify 4 with 2. They cannot be unified, so we backtrack, go to the third line, do the recursive call. Again, go into the second line, unifying 4 with 3. They cannot be unified, so we backtrack, go to the third line, go do the recursive call. Finally, we have the base case where the second list is empty, which succeeds, so we get true. Okay. Very well. So this pattern of using cut together with fail, this composition of combination of cut and fail, can be actually sort of factored out, right? So what we can do is we can do this. Yeah. Yeah. What do you think will happen? So if we pass, instead of 4, we pass a variable like x, right? That's the question. What happens? Well, you go to the second line, you try to unify x with 1. Can you do that? Yes. So you succeed, you go to the cut, and you fail. Right? Okay, so negation as failure. So we factor out this pattern into a higher order predicate, sort of. So here we use a variable which we then use as a truth value here. So what it means is that whatever we put as a goal is going to be interpreted as a predicate itself. So either true or false. So negation of some goal is it tries to satisfy the goal. If the goal can be satisfied, then we cut and fail, right? And any other goal is fine. So if the goal fails, then we succeed, right? Okay, so here's a reformulation of not member using this neg predicate. So what we have here is 2 equations. The first one tells us that if the list is empty, then we succeed. If the list is not empty, then we succeed if h is not equal to x, right? This neg is used to negate the unification. And x is also not member in the rest of the list. Okay? So what neg here does is it tries this goal. If it succeeds, then this will fail. And if h equals x fails, then neg will succeed, right? Very good. So now, yeah, we have just talked about what happens if we call not member with a variable. And yes, if we have x as our element, and we try to see if x is not a member of the list 1, 2, 3, well, because we're using unification, right? We see, okay, x is x can be unified with 1, so negation of that fails, negation of that fails, yeah, and so the entire predicate fails and we get false. The same happens if we have variable inside of the list, right? So here we see, okay, we have a non-empty list. We try to unify 4 is x, 4 with 1. It fails, meaning that neg succeeds because of its second equation, right? So we have success here, and we go to the recursive call with the list x3. In the recursive call, we again have a non-empty list, but now we unify 4 with variable x, which succeeds, meaning that the negation of that fails, and the whole predicate fails. Okay? Now, because it fails, it does not backtrack. So whenever we fail, whenever we use this neg, we use it together with the cut, which means that it actually cuts some of the other possibilities, right? Which also means that this negation as failure is not, strictly speaking, the same as logical negation, as logical not. Because remember, the way cut works depends on where it is placed, in which predicate do you use it, right? And what other statements propositions did you try before you reached the cut, right? So because negation uses cut, it is very important to understand where you place that negation, right? If you first check, so in this case, we want to first check for negation and then do the recursive call, and everything works fine. But in some cases, like with arithmetic, you want to make sure that you have instantiated some of the variables before you do the negation, right? Because if you do not have, if you did not instantiate, so for example, if you, I don't have an example right here, but if you have not member this and then comma x is equal to 4, right? So if you have not member x 1 to 3, comma x is equal to 4. Now 4 is not a member of this list, right? But you fail before that, right? And you never backtrack. You never backtrack to say, okay, x, it can be false if x is one of these, but it also can be true if x is not one of these, right? There's no representation for that in Prolog, right? To say that variable x is not one of these things, right? It's always some specific thing. So if you want, if you have some other proposition that clarifies what x is, you want to put that before you use it in some sort of negation, not after. I hope that makes sense. Yes. Yeah. So if when you enter this this negation, if you know what x is, then it will probably fail if it is not in the list. But if you don't know what x is, unification will succeed. Okay, very good. That's it